If you would recall, we've been talking about integration. Loosely, integration is going to tell us the area under a curve and above an interval on the x-axis. Moreover, we want to think of integration as multiplication, but one of the factors is continuously variable. Integration is multiplication, but one of the factors is continuously variable. In our first example, in our first picture, this red rectangle, the length is constant for the entire width. So we get to multiply 3 times 5. In the second example, the length is variable, but it's constant in short bursts. So here I have a constant length. In the second picture, we have variable length. But it's constant in short bursts. Since the variable length is constant in short bursts, we get to use multiplication in short bursts. In the previous one, we had a constant length, so we get to multiply. Full stop. End of sentence. In the second one, we had variable length, but it's constant in short bursts, so we get to multiply in short bursts. But after we multiply in short bursts, then we have to add, because that's how the area works. We break it into 3 rectangles. We use multiplication on the 3 rectangles. We add the results. In the previous one, we could think of multiplying in short bursts, but everything is the same. So that's why we got to add, because it's 1 times 5. 1 times 5, and 1 times 5. And we notice that, hey, the length is always a 5. Let's just do 3 times 5. Because multiplication is just repeated addition. When everything is the same, if we're making an addition, if we're making a sum, and all the terms are the same, we get to multiply. When all the terms are different, then we just keep adding. In the third picture, we go one step further in complication. The length is not just variable, it's continuously variable. So in the third case is the final form of multiplication, a continuously variable length. Our strategy was to just assume that the function was constant in short bursts, like just go back to the previous case. Our strategy is to go back to the previous case. That is, assume that f of x is constant on short bursts so that we can multiply and then add. So that's what we did on Tuesday. We assumed that f of x was constant and short bursts that we call delta x. That is, we looked at this area as a bunch of rectangles. That gave us an approximation of the area. And we recognized that if we used more rectangles, we would get a better approximation. And since we're doing something more often will get us a better approximation, calculus says that if we just do that an infinite number of times, we'll get the exact value. So this is going back to the previous case so that we get to use multiplication. That was the big thing. So f at xi is the function evaluated at some point, and we're going to use that as the height. We evaluate the function to find the height or the length. I've been calling it length. I assume that if the function is just flat for some short burst of width that we call delta x. That's where we did 1 times 3. Then I went to the next one. F at x2 would be 4 times 1. And then f at x3 would be 5 times 1. I just do length times width a bunch of times. Then we added up the areas of all these rectangles. Here we are adding up the areas of the n rectangles. This is just our approximation. When n gets bigger, we get a better approximation. We're increasing the resolution of our picture. And then calculus comes along and says, just keep doing that forever. And so this is the Riemann sum. It comes directly from the previous case. I want to find area equals length times width, but my stupid length is all continuously variable. So we go back to the previous case where things are easier. We flatten out. We look at a low-res version of that continuously variable function where it's flat in short bursts. So we get to multiply in short bursts so that we can add. The weirdness here is that the variable length is continuously variable. So this then we add step is really fishy because where are we going to put the pluses? Fortunately for our heroes, calculus has come along and we're like, oh, dude, if we have an infinite number of rectangles, there's nowhere to put the plus signs. We can't put plus signs in a continuum because there's no next term. There's no next real number. So fortunately for our heroes, this is a definite integral. So notice I no longer have indexing on my f of x. It's not f of xi because I can't index the real numbers. I can't say here's the first real number, here's the second real number, here's the third one. We can't make an index of that set. It's an uncountable set, so that's not available. The delta x, we're going to do the same thing that we did with the slope, where slope is delta y over delta x. The derivative is dy over dx. When those deltas become infinitely small, we call them dy and dx. And that's the same kind of dx that we have here. It's infinitely small width. So this f of x times dx is still an area. Because we now have switched to a continuum, we write a different s. Instead of writing a capital sigma, we write the integral from a to b. And this is an indication of the real numbers that we're going to plug into the expression f of x dx and then add. So that's what the integral part of the definite integral is telling us. It's giving us the set over which we are integrating. And it's kind of we're thinking of it, plug all these real numbers into this expression, then add the results. This is very suspicious because there's nowhere to put the plus signs, but calculus is, once again, don't worry about it. We got a way around this. This is where we left it last time, on a cliffhanger. Anytime there's going to be a flex day, you got to go in with a cliffhanger. So the students are wondering what's going to happen a whole extra day. I don't think that many of you spent your day wondering, how are we going to calculate this definite integral? I pretend that that's what happens. Like, oh man, can't wait to find out what happens next time on Calculus 1. I guess all this was just previously on Calculus 1. Anyway, so this expression here we would say is the definite integral of f of x dx from a to b. That's how we would read this symbol. The definite integral of f of x dx from a to b. The definite part means that we're plugging in values. The from a to b tells us that it's a definite integral. Since we're new to this integration business, y'all have to say the definite integral of f of x dx from a to b. Even though by saying from a to b, you are implying that it is a definite integral. Later on, when you've proven your worth and shown that you understand what's going on, then you can start shortening your phrase and be like the integral from a to b of f of x dx. You can also switch the two prepositional phrases. So a lot of times I'll just say the integral from a to b of f of x dx. And if you want to be really cool, if you're really sure that your audience knows what you're talking about, you're going to say the integral from a to b of f. and people will fill in the rest. You know what I mean? So you can switch around the prepositional phrases. So the definite integral from a to b of f of x dx, or the definite integral of f of x dx from a to b. You're probably going to default to saying from a to b first, because it's the thing that you write. So you like write the integral from a to b of f of x dx. That's just the order that we write it. Now, what we haven't talked about is how to actually make this calculation. So guess what we're doing today? This might be really early for this because it's only week 9, but I don't like withholding information from students. And the subject has come up before. It's like literally my job to like give you information. You've paid me for the information, now I'm on delivery. So the definite integral of f of x dx from a to b is capital F at b minus capital F at a. Math was already case sensitive, but it's super case sensitive now. Math has been case sensitive ever since you learned the natural logarithm. So if you write in all caps, that is incorrect. I'm kind of glad email has come about because it's just reduced the number of people that write in all caps. That is pretty much limited to architects now, so we're safe. No one just writes in all caps anymore because it's viewed as shouting in email, so people just don't do it anymore. You know what I mean? But if you write in all caps, you are 100% incorrect and it needs to stop. I had students that were very stubborn about it. They would write e to the x with a capital E. And I'd be like, oh, what's this capital E? I don't know what that is. And he's like, oh, yes, you do, but I'm going to pretend that I don't. And then I'm like, oh, stop using capital E. Stop using capital E. Stop using capital E, 0 out of 4. He's like, oh, how come I got this wrong? Because you wrote capital E. I don't know what that function is. Oh, if I wrote lowercase e, if I write lowercase e, will I get points? From now on, you will. Did it again. So the next time, -4 out of 4. Like, oh, this mistake is so bad, it cancels out one of your right answers. The only question now, is this a linear function or an exponential function? It does start off at 0, so that might think linear, but maybe it's piecewise. And after 1, it goes from linear to exponential. Michael, would you like to find out? Michael, not really. Then you better start writing with a lowercase e. It worked. I don't like to have to threaten people to do stuff. You know? Anyway, what are we talking about? Oh, yes, math is case sensitive. So we've introduced this new concept. We want to calculate the definite integral. And the definite integral of little f from a to b is capital F at b minus capital F at a, where f is an antiderivative of little f. This means that little f is the derivative of something. So that is capital F prime of x is equal to little f of x. Any questions? So unsurprisingly, you already know about antiderivatives. You've been calculating antiderivatives in reverse this whole time. Secretly, we were doing stuff backwards. In math class, you always have to learn everything backwards and forwards. I just decided to teach you the backwards version first. I taught you reverse antiderivatives and just called it anti-antiderivatives, and I made the antis cancel out, and I taught you derivatives. You thought you were learning derivatives, but secretly, you were learning anti-antiderivatives. I wanted to give you a head start on things. If you're like thinking, aren't those the same thing? Quiet, you. What's the derivative of x cubed? 3x squared. So the antiderivative of 3x squared is what? Oh, sorry, a good point. An antiderivative of x cubed is what? 3x squared is, dang it, you messed me up. An antiderivative of 3x squared is what? X cubed. So the derivative of x cubed is 3x squared. So an antiderivative of 3x squared is x cubed. What's another antiderivative of 3x squared? What's another function whose derivative is 3x squared? Yeah. X cubed plus 1 plus c. Some people just don't want to mess with like individual ones. You know, x cubed plus 1. You said, give me one more. They're like, oh, now we're going to give you an uncountable infinity more antiderivatives. We know that the derivative of a constant is equal to 0. So another antiderivative of x cubed. So another antiderivative of 3x squared is x cubed plus 1. Remember that the derivative of a constant is equal to 0. So the derivative of x cubed plus 1 is also 3x squared. So the general antiderivative of 3x squared will be x cubed plus c, where c is some constant. That's because the derivative of a constant is equal to 0. Any questions? Told y'all you knew how to do this already. We're just going to do our derivative stuff backwards. We're just playing the derivative game Jeopardy style. So instead of giving you a function and asking you for the derivative, I give you the derivative and ask you for the function. I'm going to put 2 out of 2, page 2 of 2, to give you hope that this is going to be the last page of notes. Also because, you know, it's the last page in the book. So. Plus, I don't think I could stand to do like 2 more pages of antiderivatives. So remind me again, what's the general derivative of a power function? What's the derivative of x to the n? Nx to the n minus 1. Nx to the n minus 1. So let's write down what things that we did in this operation. This operation says multiply by the exponents, and then subtract 1 from the exponents. So this operation says first multiply by the exponents, and second, subtract 1 from exponents. So if we're going to do the inverse of this, what's the inverse of multiplying by the exponent and subtracting 1 from the exponent? So if we're going to do inverse operations in reverse order, first, we'll add 1 to the exponent. And then what will we do? Divide by the exponent. That is how we invert a bunch of operations. We do inverse operations in reverse order. If you start with bare feet and step 1 is put on sock and step 2 is put on shoe. Let's pluralize that, otherwise we're doing sock, shoe, sock, shoe. Step 1 is put on socks and step 2 is put on shoes. Then to undo that, to the inverse operation will be step 1, take off shoes, step 2, take off socks. The shoes have to come off first. So the order of the operations here is to multiply by the exponents and then subtract 1 from the exponents. The inverse of that in reverse order will be add 1 to the exponents and then divide by the exponents. We're just flying through notation today. This is an indefinite integral because I didn't say from A to B. This is just the integral of x to the n dn. And we're going to follow these instructions. We're going to add 1 to the exponents. And then we'll divide by the exponents. Then we're going to make a distinction, since I'm just doing an indefinite integral. Here is an antiderivative. So let's suppose I want the general antiderivative. So not just an antiderivative, but specifically the general antiderivative. To get that, we write plus c. If x to the n is the derivative, it must be the derivative of 1 over n plus 1 times x to the n plus 1 plus some constant that got zeroed out when the derivative happened. We call the plus c the constant of integration. We don't know what was there before, because when we take the derivative of every constant, we always get 0. So we know that the function looked like a x to the n plus 1 over n plus 1, but we don't know what the constant looked like without additional information. If you think back, when we first started talking about area under the curve, we say the derivative, if the derivative is positive, then the function is increasing and the area tells you how much. All we know is how much has changed. We don't know where we ended up. I drove at 80 miles per hour for 5 hours. I was 400 miles from where I started, but we don't know where I was. We don't know what the starting point was. We don't know what plus c was. That's the plus c. That's us not knowing where things started. That happened because the derivative of every constant is equal to 0. So we lose information when we do the derivative. So this indefinite integral stuff is almost the inverse of the derivative. So we could talk about an antiderivative or the general antiderivative. Any questions? How's everybody okay? If you're stressed out because it's only week 9 and this is not supposed to happen for until week 12, that's okay. Don't worry. I'm a professional. Don't try this at home. Like if you were just like reading through the book, you wouldn't want to do things this early. But it's all right. It's all connected. So let's just keep connected. So just from a notational standpoint, I like to write 1 over n plus 1, x to the n plus 1. Some of you will not like this. And you look at a different YouTube and look at x to the n plus 1 over n plus 1. This is the same. I'm not sure which phrase is going to make you remember this better. I just don't know. Some people are going to prefer the 1 over n plus 1. Some people are going to prefer saying over n plus 1. Some DMs don't like letting players use a potion as a bonus action. But others are fine with it. Incidentally, it's a bonus action. You roll, that's when you roll. But if you do an action, you just get the maximum amount. So I'm not sure which one you're going to remember better. Just pick one. My personal favorite is add 1 to the exponent, divide by the exponent. I'm not very good at mnemonics. My mnemonic for the trig functions is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. That's my mnemonic device for remembering my trig functions. What is the general antiderivative of x to the 5th? Just add 1 to the exponents and divide by the new exponents. This is a little bit unfair. I didn't talk about properties of antiderivatives or properties of indefinite integrals. But that's okay, because this is just antiderivative. So the same rules apply. If I multiply by 7, just keep multiplying by 7. Constant factors just get carried along. The same a lot of the same strategies that we use for derivatives at the beginning are going to be in play for antiderivatives. we read the square root of x in its improved form as x to the 1/2. Then we can add 1 to the exponents and divide by the new exponents. A lot of this is just going to be recycling old material. This is called the Disney strategy. Just recycle your old material. Don't come up with new ideas. Recycle your old material. I'm still waiting for Disney to come out with a calculus movie. That way they can copyright it. And all calculus will just be owned by Disney now, because apparently that's how it works. Like, you can't make a Snow White movie. That's like an old story. Disney didn't invent that shit, but they're like, oh, if you make Snow White, we're going to sue you. Like, well, that's like an old story. It'd be like, they're going to find out something that happened in your family, make a movie about it, and then you can't tell that story anymore. So I'm going to make a movie where I tell the story of my family. And Disney is like, oh, no, you will not. We bought that. I'm waiting for Disney to buy calculus. Anyway, we're just going to retread all the old stuff that we did. X to the 1 over x to the 5th. We're going to write that as x to the -5. Add 1 to the exponent, divide by the new exponent. Yeah, so -5 plus 1 is -4, and then we'll divide by the new exponent. Question? Yeah, it's like the third trilogy for Star Wars. Oh, let's just do the same stuff. Then the one in the middle, they're like, oh, hey, let's try something new. And everybody's like, oh, no, don't do that. Then they just go back to doing old stuff. Let's just go back to doing old stuff. It doesn't make any sense, but you know, that the fans will kind of like, as long as they don't think about it too much. Which is fine, actually, because the fan base for Star Wars is going to complain anyway. The worst thing about Star Wars is the friggin' fans. If you're working on Star Wars, any Star Wars product, just don't listen to the fans. They're idiots and they're terrible. And no matter what you do, they're just going to hate it. So just flip them off and do your movie.
When you get 0 off it and get the result.
I don't have enough money or power. I'm beneath Disney's notice, so I can get away with talking a lot of shit about Disney. What are they going to do? Ban me from going to Disneyland? It's like, oh, if we ban Leach from going to Disneyland, then he won't spend money at Disneyland. He's only got 2 of the 4 lightsabers that you can craft at Savi's workshop. He's only halfway through the most expensive pin collection that you can get at Disneyland.
You cannot milk them for money.
Uh-oh.
It's like, it's actually just 1.
Yeah, if I add 1 to the exponent here, this doesn't work. What is it? ln(x). Thank you. Whew. That was close, because we're over time. So that's okay, because the derivative of the natural log of x is 1 over x. So that tells us that the antiderivative of 1 over x to x is natural log. There's a little twist to it, absolute value of x. This makes the domains match. Now we can do the antiderivative of any power function.
Awesome.
All right, that's going to do it for today. I will see you all on tomorrow. Hopefully I'll get bought out by Disney. I'm open to negotiations, Disney, but I don't come cheap. That's it for today. I'll see you all on tomorrow. Have a good day, and thanks for playing.
Bye. Have a nice day.
You too.